So a few words about the earthquakes now, for those of you who are interested in that, the seismic information. So what happened during the eruption is we had intensity changes. So there was initially earthquake activity quite strong, and then the eruption started here. This is a timeline of the eruption, and then it was going up and down a little bit, and up again and down again and up again and down and up, and several times. And it was actually really frustrating for the population, because the people thought, oh, it's getting weaker, and then it got stronger again. Oh, it's getting weaker, and then it gets stronger again. And this is a real problem, and I think we have to do a bit more research on that, why this is happening. And I have some idea, I'll mention it later. But here we have the earthquake depth, and this is longitude and latitude. And there seems to be some major area of earthquakes here at about 10 to 15 kilometers depth, and about another one at 35 to 45 kilometers depth. And we have to assume this is where the magma was sitting prior to the eruption, likely in two levels, in two magma chambers or reservoirs. And I suspect this is the reason why things are going up and down, because if you have two systems connecting and they're feeding into each other, it probably causes a bit of a jam every now and then. And this is my hypothesis, at least. So, and here you see the timeline, the date down here, and you see the earthquakes. This was just before the eruption. The eruption started here September 19th. So this is earthquakes of the magma rising up to the surface. But during the eruption, there was earthquakes in this level, this upper level, and in a deeper level here. So again, picking out two main areas where things must have been moving, and presumably this is the reservoirs where the magma was stored and withdrawn from. So, and yes, this is the size of the magma chamber or the reservoirs. We get an idea here. The lower diagram is again the up and down, and my suspicion is that the interaction between these two reservoirs, that's what's causing the ups and down. But we have to do a little bit more work to see whether this is actually true. So here is the intensity of the earthquakes. This is the earthquake magnitude, and here we're reaching up to about magnitude 5. That's serious shaking, magnitude 5. So things are falling off the shelves at that. And the strongest earthquakes were actually in the deeper reservoir. So the deeper reservoir was feeding towards the end, and towards the end of the eruption, the deeper reservoir was the main contributing reservoir. And we'll see that also in the chemistry. I come back to this just in a minute. For the people who are interested in rocks and geochemistry, I'll spend a few minutes on that as well. So this is the geochemical part now, and you can take rocks and put them under a microscope, and then you see little crystals there. And if you change the light, if you polarize the light, the crystals come there depending on their chemistry in different colors, which helps the geoscientists to work out what crystals we're actually looking at. And early in the eruption, we had just a few tiny little crystals, the beige colored and pink guys here. But towards the end, the crystals were getting bigger and bigger and larger. So this was a very important observation. It tells us that we were taking magma from deeper and deeper within the system. And this was a useful thing to realize. And we also had these strange white things, the xenopumices, as I mentioned them earlier. And here's just a few images from the microscope. And also with the electron microscope, we have different mineral types. At the beginning, we had a mineral called amphibole that has a bit of water in it. Towards the end of the eruption, we had no amphibole anymore. And amphibole grows usually at about, the level just under the volcano. And towards the end of the eruption, when the deeper reservoir, the deeper magma chamber was contributing more strongly, we didn't have that mineral anymore. We had mainly another mineral called olivine. And this is the olivine here. Here's an example of this chap here. And this tells us that likely we were sucking magma from deeper and deeper within the system under the volcano. And at some point, the magma was exhausted and the eruption stopped. So this also gives us a hint to better understand how long these eruptions will actually go on. There's a limit to them, because during the eruption, people got really frustrated, saying, when will it end? When will it stop? And nobody had an idea, but this actually tells us something. I think we can monitor the minerals, and this will help us in future to say something about when things are drawing to an end. So here's some useful things for the future. So For those of you who are into geochemistry, this is just the classification plot. And here we have silica against total alkalis. This is older eruptions in the area, 1971, 1949, etc. And this is the eruption that we had in 21. It spans quite a spectrum, more than the previous eruptions. We had these white guys, I mentioned them, these xenopomaces. They're completely off. They have nothing to do with the volcano itself. They are clearly not related to the volcano directly, and they are older sedimentary rocks, likely from the ocean crust, that were brought up accidentally. But that is actually good for the geoscientists, because it means you can look at the ocean crust without having to drill a hole. The volcano has helped us to look at some of these rocks. It brought them up for us. So, and here we have the rock chemistry over time, and we don't have to go into details, but here we see the dates for the rocks. Here's the individual dates on the right-hand side, and we can see that with continuing eruption, the chemistry was changing. The aluminium content was going down, the magnesium content was going up, and magnesium is a good sign for deeper, more primitive, as we call it. And indeed, this is consistent with the lower part of the reservoir system contributing more and more during the eruption. So here we have good indications of how magma is sucked into the volcanic vent with time over the 3 months of such an eruption. And here we see different chemical parameters changing with time. Here's magnesium. It's rising up during the first few days of the eruption, and then it stays constant. Aluminium is going down, and then it stays constant. And here we have calcium rising up almost consistently. Total alkalis going down and then staying rather constant. And this is very informative for us, because I think what we're seeing is that this initial part is magma from the upper reservoir, the 10-kilometer reservoir, and then we're drawing magma more and more from the deeper 35 to 40-kilometer reservoir. And here we got the first isotope results. They're fresh from the lab, and here we have oxygen isotopes. There's a lot of oxygen in rocks, so this is very useful. And normal Atlantic Ocean crust is about following this line here. But what we see here is there's a bit of wobble, and then we are hovering around this line. So this is very interesting. It coincides with this change here. And I said my hypothesis is that this comes from this upper reservoir at about 10 to 15 kilometers. And well, in order to explain this wobble here, we have to look a little bit further. So here is some work I did many years ago about how the ocean crust actually has oxygen distributions. And what we see is there's some low oxygen data and there's some high oxygen data at different levels in the ocean crust. And here we have a distribution on the left-hand side here where we're going down and up at the same time. So it would imply that our reservoir was sampling this material. It would have sat right in the ocean crust at this boundary between the low and the high ocean crust material. And I think we're on to a winner here, because this is previous work from a guy called Klügel, and he measured the ocean crust under the island lying at about spot on 10 kilometers. And this is the seismics again, and it's a bit small, but this is the 10-kilometer range. So the seismics is consistent in the geochemistry as well. The first 10 days of the eruption was drawing magma from the upper reservoir, and then we must have drawn magma from the deeper reservoir. So this gives us a great understanding of how these volcanoes are fed. This will be extremely helpful for future eruptions in the area. So this is the model, therefore. We're starting off bringing magma up from this upper reservoir, and then increasingly we are tapping more magma from depth. This would explain the distribution of the earthquakes as well as the geochemistry.